Hello, everyone. Today we are going to talk about more theoretical part of sequential data processing. And in particular, we consider different stochastic models and how one can justify usage of such models in different scenarios and why we even need them when we right now can do practically everything using deep learning. These slides were mostly prepared by Evgeny Burnaev, and I'm happy that I can share them with you with his permission. And so let's start the lecture and give some details on these particular models. We start with a general motivation on why we need these particular models and what we should focus on. Then I will introduce some particular models that are of the most interest to the community related to time series processing when we are talking about classic models. Then we will have another part about the main assumption maybe in this area about the stationarity of time series data and on how we can translate the stationarity, check it, and if we can ensure that the time series is more or less uh, under this assumption, how can we apply maybe one of the most popular models in this area, after regression moving average or after regression and integrated moving average. And so let's start. And so I will start with the general motivation of why do we need this thing? Why do we need time series data? And so let's start with an example. This is SP 500 index for about half an year. And for this index, we see that it has kind of strange structure and a lot of peculiarities. And also it's particularly obvious that we need to work with this data to extract some value of it. For example, we can try to predict this data. We can also estimate on the confidence intervals for any part of this data, or we can try to extract some embeddings of the data as a whole. And as this time series is pretty simple, we don't have much here to discuss. We can try to model explicitly what we want from this particular uh, time series, and we have a lot of points to cover here. The first one is compact description of the data. In this case, we want to, for example, uh, go from this like a lot of measurements we have in the data to like maybe one or two coefficients that represents the main properties of it. And so we can compare one time series with another time series and say what's if one is better than other, or we can say what is the closest time series and what is the closest station to what we have right now when we are talking about some market. Also, as long as we can provide a consistent models for time series modeling, we can try to create some interpretation for the results we obtain. For example, for these coefficients we extract from the data, we can say that right now it works good, but later it works not that good, and so on. From the problems that are related to the description of what's going on with time series, we can try to project what we know to the future and try, for example, solve a forecasting problem. In this case, we have some time series, for example, and we want to continue it in the future. And this prediction should be accurate. So if you have like true time series, it should be close to what we have as our prediction. After forecasting, so we can say that this true guys is about like descriptive modeling. It's kind of not yet prescriptive, but it describes on how, okay, like predictive modeling, I would like to say here. Later, we can try to do prescriptive modeling. So we can try to identify what we should change to make the behavior of a particular time series better. And in this case, we are we like encounter this control theory and this control problems. But if we are talking about machine learning, for sure, we don't have much to worry about, I suppose, in most cases. And the control approaches are pretty simple. for most cases, but for sure we can apply this wide range of tools available from control theory to make these results even better in some cases, especially if we have this like theoretically deep understanding of what's going on in our time series. Last but not the least, we can try to check something about this data. Maybe it's related somehow to the first point and to the second point, and we test if the time series is stationary or what it will be in 1 month, and we is this situation similar to what we have before. And also, as we have these fully controlled models, we can try to run the simulation and try to evaluate different scenarios and describe what's going on and what will go from this particular moment in the future. For example, we can change one control parameter and say that it's quite probable that we will have time series like this. This is like the first scenario. And also we can try different scenario for different set of control variables or different station about what we don't have right now. And this is what we also can do with this simulation part of objectives for time series analysis. Let's try to start with some decomposition and with some classic model on what time series is about. A good example and like pretty common example of time series is this data on monthly sales for a small shop at a small town in Queensland, collected more than 20 hours ago. From what we can see, we can identify these peculiarities of the data that we will later reflect as the model structure. We say that we have right now these peaks. These peaks all are about the end of the year. So we can say that we have some periodicity and the period for this data is about 20 months. Also, in addition to the periodicity, we have an increasing trend. We can say that each year, this peak is slightly larger than it was last year, and it holds not only for the peak value in December, but also for the general trend in the data we observe. So we can say that we have increase in sales, and this small shop is very successful. But this is what we should include in our model assumption for a model for forecasting, for example, of the sales to be accurate. But what also we can see and what complicates our time series analysis is that it has different scales during different years. We say that in the beginning it's like below 20,000 and even maximum value is below this particular value. But as we observe more and more data, we have increased like about 5 times. So, okay, to make the analysis proper, we normalize the data, and after normalization, we have something like this. In particular, we use log transformation, so we take a logarithm for each value we observe in the data. It's a legitimate operation because for each value, it is positive just because it's amount of sales, and this amounts are always greater than zero. So after the transformation, we have transformed data like this. It looks like more uniform and we don't have this sharp increase. We still observe the trend is increasing, but we are still happy that it's not like 5 times. It only linear scale changes. Okay, we normalize the data, make it look more stationary, and we will talk later about what the stationarity is and why it's so important for this particular case. But now we want to try some model, and usually, if we don't have much data, we use modeling of the trend with a linear model, and here we observe linear increase in amount of sales for this particular data. This is our observations we had here, like this, and this, and this, and this. And we fit a linear regression model to it, and we observe this uh, blue curve that help us to identify what is the trend in the data, and we observe that it increases in general. And also we can, I hope in this case, justify that the coefficient for the linear regression, this angle on how big the increase is significantly bigger than zero, and it's even statistically significantly bigger than zero. Also, after application of these two operations, normalization and trend extraction, we can try to analyze what's left, what we can't explain with this quite smart and reasonable model. In particular, we can look at the residuals. In this case, this is the difference between the trend value we predict. Okay, let's say it y hat for time t, and the true value we observe from our data. We can use an absolute value of this difference, or we can still see only the, okay, not absolute values, and so we can observe here, for example, negative values. That helps us to understand that sometimes we don't estimate this trend quite well in terms of both increase and increase, and we can specifically analyze here why do we observe such behavior. In this case, it's pretty obvious. We have these peaks related to the end of the year, and we have this peaks, but of the other type when we look at the lower part of the graph here. And in January, I suppose no one buys these groceries or whatever this shop sales, because maybe no one is traveling in January, and or they spent all of their money devoted to souvenirs last month. But whatever, we can try to adjust the model to take into account that we have these residuals, and we can try to explain it in ways common to time series data models. For this particular case, we say that we want to identify seasonal variation and include seasonality in the data. So if you look at the previous guy, we can say that we can repeat the same pattern each year after year, something like this. So it has the similar up and down values. And also it has kind of few parameters because we don't need to model each data point explicitly. We model only one period that we assume is presented in the data. So after adding of this periodic seasonal variation, this periodicity to the data, to the trend, we have something like this. And as we can see, it's pretty nice, much nicer than we have only with a linear model, or without any model at all, or without scaling and so on. And we also see that all these steps are essential for this particular data. And it's quite common that we observe such behavior in many different time models. So let's see how we can apply these objectives to this particular problem of working with souvenir shop sales for about 10 years. We say as a start that we have a decomposition of the data to a number of components. Here we introduce three components. Two components we talked about explicitly, like trend, X, seasonality, S, and noise we haven't talked yet. But it's pretty obvious that it is presented and it can be interpreted as noise itself, or is something that we don't have enough knowledge about. So after the representing of the data in this way, we can try to interpret what we have. For example, we can say that we have seasonal adjustment here, and we need to enforce it, and we can even try to base our decisions of what we have, or somehow measure some macroeconomic indexes on the base on the sales in this small shop at the shore or somewhere in United States, or maybe not even United States. We can go on and try to do some predictive analytics For example, we can try to predict sales next year. So we can plan logistics, we can plan how much order should we do, and so on. In addition to this, we can try to use all these guys together. In this particular case, maybe it's not that important, but for example, for control, we can try to say that maybe we should hire another guy here, and we can assume that we will have more sales if we hire additional personnel to help this shop, and so on. Let's also check on another popular dataset. It's mainly number of unemployed people in a very distant island, and we can see that it also has some peculiarities we later explore. For example, we can try to again see the trend, maybe some periodicity here, who knows if this peaks are at equal distance or not. We can check it using some simple statistical tools. And also we can try to have some additional components if we need them. And let's see what we can do about this particular time series. At first, we observe the trend, and trend is pretty easy to grasp here. And again, we see that we don't even use this log transformation because the variable, this unemployment, number of unemployment people is quite similar because, okay, I think that the total number of people is similar, that the central bank regularizes the interest rate for other banks, so we don't have different significant changes in unemployment and so on. But we still have some macroeconomics that leads to the decreasing of the number of unemployed people for this particular data and for this particular country. And so we start with modeling this data with a linear trend. Okay. Again, we can try to adjust some periodical component of the time series. And as we can see, it's also pretty easy to grasp and pretty easy to agree that we really have this 1 year periodicity, similar to what we had with this sales data. And in the end, we have something that similar to what we have before. Also, when we are trying to match the objectives of time series analysis with what we have and what we already done for this type of data, we observe three trends we already encountered during this lecture: trend, seasonality, and noise, and one additional component that can be related to some latent variable that is not known, that's not presented in particular for this time series, but it's pretty obvious affects how big the unemployment rate is. For example, it can be some policy uh, for this country, or maybe even policies adopted worldwide, or it can be like a binary variable that reflects do we have a pandemic of COVID-19 or not at this particular moment in this particular country. Also, we can try to interpret this data. Let's say that we have these variations related to seasons each time. So we can try to account for it and make either model more precise, or maybe we can try to use it in a practical way to reduce unemployment or to correct the policies we have to make it more optimal with respect to the total success of the country. In addition to interpretation, we can for sure do a forecasting and predict unemployment rate in the future using the model we have right now, because for trends, it's pretty easy to continue the trend as a linear function, whatever long we want. For seasonal components, we also pretty easy can have something like what we had before, and so on. And for these macroeconomic parameters, we also can try to model them in a way, add this part of the model to our future observations, and have in the end quite nice plot that reflects our expectation about unemployments in the future. When we try to make it smarter and more useful for the population of the country and for the country itself, we can, for example, control the monetary policy and check how it affects the unemployment. Also, we can go in a different direction and try, for example, test do we have a global warming or do global warming affects unemployment rate in Australia? Okay, whatever. Also, we can try to identify some particular patterns related to catastrophic events. And for these catastrophic events, we can try to estimate probability for them on the base of the data and simulate maybe some scenarios and unemployment rates if some mm, event related to a natural disaster happens. So we see that we can pretty easy link time series data to these particular points about the objectives of time series analysis, and that in many cases it's pretty easy to spot something like this in the data, and we often don't need quite complex models. So in this case, it's enough to have this seasonality component and linear component, and this all we can do without neural networks. We don't need to learn the presentations. If the data is simple enough, or we have an expert then can provide some advice on how can we select the model. Okay, for sure, with the help of a machine learning specialist. But let's try to formalize in more details what we can say about time series data. And so let's define it in the most general form in the very beginning. We can say that if we observe some values, and yes, these values are random because it's time series and we have some noise, for example, we can model the distribution for the for the whole sequence here. So we have a sequence like this. Each time we observe yt1 up to ytk, and so we have a joint distribution for each, and for example, can identify a cumulative density function for this multidimensional random vector that is identified by this upper bounds, and so we have the probability for zk to get this particular vector. Also, if you try to have a general model, in many cases it shouldn't be very useful because it would be too broad, too wide, not of any practical use, too many parameters. And also we can't achieve goals specified before. For example, if you have too complex model, it's pretty hard to interpret this model. And so we are left with something we can interpret and okay, sad story. So let's make it a bit more happy and try to restrict our attention to more useful in practice models. And what we usually do in this case, we identify the mean value at each time step, and we identify correlations of values between neighbor or far away observation here. So here is, for example, yt1, and here is the correlation between yt1 and yt2. And so let's start with specification of the simplest possible model of white noise. In this case, we assume that each value of y is independent and equally distributed random variable with some mean value and some variance. In this case, it's pretty easy to see that we have the decomposition of this probability to the product of probabilities related to the specific points in time. We can say that we have independent random variables. So the joint distribution equals to the product of a one-dimensional distribution specific for each y here. And so we can say that this model is pretty simple, and it's quite easy to imagine that we maximize this point with respect to some variance, for example, and some mean value if we use sorry, if we use some mean value instead of what we have before, 0. But also we can say that this model is pretty useless for almost all use cases we can imagine. Let's try to understand it for the case when we are forecasting something. You can say that, okay, if all variables are independent, then this probability equal to this probability. It doesn't depend on all previous values because all random variables are independent. So we can do anything interesting about forecasting. Maybe in very specific cases it can be useful, but in general it's almost a useless model. Let's just say that we don't have any dependence, and actually we can look at this time series as a number of separate events. Not very inspiring example, but I suppose pretty simple here. For sure, we can try to make the model more complex. And we, for example, can use the random walk paradigm here, the random walk model. And what this model is about. In this case, we say that each observed value is sum of kind of large number of different noise values. In particular, we can say that for each epsilon, we have observations of it, and y is the sum of epsilon at each time step, with each epsilon is generated from some Gaussian distribution with specified mean value and specified noise. Also note that this kind of usage of white noise model, but in a more clever way, because right now we can say that this epsilons, actually the series of all epsilons here is white noise. But if we sum these values, then we no longer observe white noise. Instead, we observe the quite interesting and quite realistic dependence of each pair of yt and some past value of it minus 1, for example. And we can say that in many applications, these are quite reasonable assumptions to have this random walk time series model. For example, it can be stock prices on successive days when we observe a molecule that goes through a gas or a liquid, or we see that we have an animal that travels through like a forest and searches for prey, and so on. And in all those cases, it's a reasonable model, don't have much parameters, and so on. So let's try to imagine something different. We can try to use as trend and season models, as we already know that can be crucial to have correct trend model and correct season model. And so we can say that, for example, our trend would be some linear function as we expected before. Our seasonal component is something identified by harmonics for cosine and sine function. And for the noise, we can here introduce any interesting model. We just say that noise is just noise. Let's don't talk about it too much. And after decomposition of like this, so decomposition of our time series to seasonal model and to a trend, we are ready to provide some description of our time series and also even some predictions. So for data we have, I don't know what this particular data is about, but it doesn't matter too much. We have this linear model here, like this, and it's pretty easy to see that we can do it, and we can try to make it work even for this pretty noisy data. Also, we can try to go one step further and estimate parameters for these guys on periodicity. So this is the coefficients we estimate. Also, we can try to select lambdas, so the period of the time series, uh, in a uniform way using some expert knowledge. Also, we can try to optimize it, but I suppose that this is something that it's not a very good optimization problem, and I suppose it's a very rare case when we try to adjust the lambdas to make the time series look better. So no one does it. So to sum up, we tried to introduce some models for each part of our training data, and we actually do it like this. We started with spotting of time series and looking for some components that are vital to the model of time series in general. Trends, seasonal components, changes like abrupt one when we like observe one time series up, and we have another one, and so it is, and we should somehow reflect it when we are working with time series like this. There can be other example here. For example, we can have outlier here, 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 and here, and we also should include this knowledge about the model here, because otherwise it would be quite risky to make any reasonable assumption and any reasonable time series models because of the limitation, because we wanted these models to be as simple as possible at the cost that we don't make them like bad, so they should fit to the data quite well. And so after plotting time series, looking at it, analyzing it with an expert, usually we start with transforming the data to make it stationary, and this is what we talk about later, why it's so important. It's from theoretical point of view and also from practice too. So we estimate a subtract trend and seasonality. Another useful trick is differentiating. So suppose we have time series like y1 and yt capital. Then we can try to look at something like yz1, zg minus 1, and each z is one step difference. Zg is zt plus 1 minus zt, and in this case it's pretty easy to model it like this. Also, it's useful to have some nonlinear transformations if you observe that we have like exponential trend and we want to make it look smarter and more better. And also what's crucial, what worries us a lot, is that if we identify the model, now we can fit the model to residuals to make it look better. And so be it. Let's provide another example of what we do here. And so we have this monthly sales data. And as you can imagine, it's pretty important to have this logarithm scale here. And after this, we can work. Another important part of the processing of time series data is taking the difference between neighborhood values. So here we observe some trend. After differentiation, we observe almost no trend. It's pretty easy to model something like this when we are talking about the data itself. What else we can do as tricks? We can try to make it look better and make it look more reasonable and more useful. And this is like what I had before as zg minus 1. We can designate as delta yt, the difference between the current value and the previous value, kind of estimate of a derivative, we can say, and so on. And for a particular reasonable time series models, we can observe what this difference is and how it's related to this difference variations. So for example, for yt that has this polynomial structure, polynomial model, so each time t we have this t plus 1 and so on. Then we have the model like this for the difference of keys order for our guy y, and also we can try to imagine on what's going on for another example of more classic decomposition to the trend, to the seasonality, and to the noise, where S3 have the period t, and we observe the difference between the value here and in these steps. So it's like yt plus d, or yt and yt plus d. Then this difference has for sure the form of t minus d, I'm sorry, and t here, like this. And also, if the noise is not id, we add this difference for a noise, and as the value of st equals to the value of st minus d, then when we are doing the subtracting, it cancels and we no longer have the seasonal component. This is one of the reasons why we even need this kind of behavior. So we looked at some models and provided some useful examples on how these models behave. And now we are ready to go to the next part and in more details discuss the stationarity of the data and what does it mean. The most strict definition is strictly stationary time series, and it holds if for all value of keys and for value of time series and for all zetas, we can have the decomposition like this. If we shift to, okay, from the present to something like present plus ash, so time series like this and time series like this, of the same lengths, then the joint distribution is the same. And we have no change here in the distribution. But it's quite hard to check. Do we have the same distribution? So instead we use a simple model for stationarity. We will consider only first and second order properties here. So suppose we have a time series and expectation for at each time moment is smaller than the infinity for the square of the y. And also we have some mean function and some after covariance function here. For mean value, okay, we suppose that we have some mean value related to each particular time moment, and we have some after covariance function related to two selected moments of t. It can be, okay, here it is a covariance that is defined as the expectation of y minus mu related mu and yt minus mu t related to it. And so we can say that y is weakly stationary if mu, the first moment, is independent of t, so we have the same mean value during all the time series, and also the difference between, okay, the covariance function is also independent of t when we shift to it. So the same function depends only on the difference between t plus ash and t, depends only on ash. For each ash, it's a particular number. In that case, we can, for example, replace these more complex designations when we have two terms, ash and zero, to the case when we have only one term related only, okay, to this time difference ash here. So we are pretty happy about it. And we can go further and say that we are interested in after correlation function. And the after correlation function equals to the ratio of the correlation function for the difference ash divided by the after correlation function for the difference 0. And in this case, we say this is a correlation, and we are interested in particular correlation. Let's see if the examples we discussed earlier are stationary or not. We start with identical distributed independent noise with mean value that equals to 0 and the variance that equals to sigma squared. In this case, it's pretty obvious that mu t equals to the constant, and also we can look at the correlation function. And the correlation function has like sigma squared value if h equals to 0 and 0 otherwise. This is pretty much expected for this white noise scenario. So this white noise. Also, let's look if we can pass our checks. We see that mu is independent of t, and gamma is also independent of t. So we can say that we have this stationarity, weak one, for this particular model. So it's pretty easy to check that. Okay, I suppose that white noise has almost all nice properties we would like to have for time series. The only problem is too simple to model something useful. Let's have another example and check if the random walks follows this assumption about the stationarity, or for our particular case, we consider weak stationarity. We say that our y is sum of independent epsilons, and each epsilon actually is a part of a realization of a white noise. And so we say that our mean value is 0, and also we can now say something about the variance. As these guys are independent, variance of sum of independent random variables equals to the sum of variances of these independent guys. And as a result, we have the variance that equals to t times sigma squared, because each epsilon has this form. Okay, let's calculate the mean value and covariance function. For mean value, we already have 0, so it's pretty easy to calculate it. For the covariance, it's a bit different. We say that this guy, the covariance between yt plus h and yt, equals to this covariance. So this is what we already have. And this is an addition we have for because of these additional terms later, from t to t plus m to t. And so these guys are independent of yt, so we don't care about them. What's left is covariance between yt and yt. Okay, the same covariance, t times sigma squared. So mu t equals to 0, and it is independent of t. Gamma is not, because it depends on t, not only on us. So you can say that this fixed stationarity does not hold for random walk. So we can try to make it stationary and consider not y's but epsilons instead. And we go back to the case of white noise. So after normalization, we can go back to the length of stationarity. But for this particular case, simple check shows that this time series is not stationary. Okay, let's look at one of the most popular models in time series modeling, after regression and moving average, to conclude the lecture we have right now. We start with a simple but quite effective model for a time series. it moving average or moving average one process because we have only one component here, and it equals to the sum of the noise here plus noise at the previous step times theta. As each epsilon is a part of a white noise process, we can evaluate the mean value that equals to 0, and also we can try to evaluate gamma. And for gamma, we write it as the expectation of these guys because the mean value equals to 0, and so it's like this. And also as epsilons are independent of each other, we have three possible cases. Either h equals to 0, then we have this guy for sure, because we have sum of two independent variables for each of y, and they're actually the same independent random variables. If h equals to +1 or -1, we have this intersection, but with a coefficient theta, and so we have the variance that equals to this guy. Otherwise, these two random variables are too far away from each other, so it equals to 0. So, as you can see, mu doesn't depend on time. Gamma also doesn't depend on time, only on h here. So we have a stationary time series. Another interesting process we often talk about, it's pretty natural way to think about time series, is after regression. It's about that the next value is the previous value times some phi plus noise. As usual, we assume that this noise is a white noise with Gaussian random variable of 0 mean and sigma squared variance. If phi is smaller, phi is smaller than 1, then it's kind of condition that this time series is stationary, but also we can try to identify the mean value that equals to 0 again. And also we assume that for each time moment, the covariances shouldn't depend on time moment t itself. So we have this equation here. And so it should be like this, because this variance should be the same, so x phi squared x plus sigma squared, and so sigma squared equals to x1 minus phi squared, and so we have the formula like this for this mean value, and so on. Also, we can try to calculate gammas if we assume that we have stationarity. And so we can rewrite y in this way. Then it is like this, because this white noise that isn't related to y, so we can put phi outside of covariance. And so we can say that each time we increase step by 1, we multiply the value of gamma by phi. And so it's like this for each value of h. And if we substitute, I'm sorry, gamma y of 0, then we have this formula for gammas. And we can look, for example, at some after regression process of the first order. First order means that we have only one term here. We don't have terms like phi2 by t minus 2 and so on. The first term after regression. And it's like this. We can increase phi. If you have, decrease phi, I'm sorry, we will be closer to white noise if you have large variance for this white noise, for sure. Also, we can try to have more components here, and it's kind of smoother, and we can prove it later. And so we have another examples of two popular stationary time series models. And also, to conclude, we have a nice tool to identify how stationary the time series is. We can calculate this covariance after covariance function using the sample we have, and what we can say, mm, it's like this, and it equals to the after covariances that we calculate from the data we have. So we have sample variance and sample autocorrelation function, and can look at it for some popular models we already discussed today. For white noise, we can see that this component is large. All other components are small enough, and actually this value is behind this give hypothesis testing bar for that if the correlation is more than 0.2, then it's not significant. And what we can see that we can do identify only one significant component related to zero, related to the time series itself, that is kind of correspond to lambda squared. If we try to do the same thing for other autocorrelation functions for other processing, we can say that for trend we have slow decay of sample autocorrelation function. For periodic time series we have periodic autocorrelation function. For moving average and after regression we have a bit differentiation. For moving average it equals to zero if our time window is larger than the order of moving average. For after regression we have exponential decrease of the autocorrelation function to zero if we increase the hash here. And it's pretty easy to see from the plots. Pretty easy to imagine that we should have something like this. If we have a simple linear trend plus some noise, the correlations is like this. Okay, what we would expect. Also, we have this difference to like trend autocorrelation function because of we have noise here. If we have periodic time series, we also can observe that right now we have this periodic high values of covariance function here. For moving average, it's pretty easy to calculate it like this. So you have only small number of non-zero components. For after regression, as I told you a couple of slides before, it has an exponential decrease here. Finally, we can try to generalize what we have for moving average and after regression and the order of these two processes related to the number of steps that after regression new component depends on from the past, and that is related to moving average cast steps one side, cast steps other side. And so we can say that if our time series is stationary process and if it's ARMA process, then we have the decomposition like this for our very important voice noise. Also, we can try to estimate the parameters of after regression. Particularly, we are interested in phi related to the correspondence between neighborhood values. And we can do it similar to what we have for linear regression, actually. It has the formulas like this in the end. So this is a simple but very effective models that can model many common relations between time series. You can try to use it in a different way and use a nonlinear model for it. And we are going closer to the world of machine learning because we don't know the true dependence between YG and previous values of Ys. And so we can try to train F in a very common way that everyone of you, I suppose, was doing long times, but in the end we have gradient approach and solve it. But now we can try to do some in a nonlinear setting, but okay, we can see if it's a good idea or not for a particular case. So what we actually did, we give an overview of classic models and classic assumptions and how to check them for time series models. We understand that this quite understood that this question is very important, and in a simple terms we can try to have quite complex models. And for this model, we even they are quite simple. You can do check for stationarity and kind of use more complex models. That's kind of union of the models we have before. After regression and moving average model, in my opinion, is kind of like a linear regression, but is more specific to time series we are working with right now. Thank you for the attention, and I hope you enjoy.